Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good day to all. First of all, I would like to thank the organizer, MACE committee, for giving me this opportunity to share my research work today in MACE Monday TED Talk. Today, 31st of May, 19th of Shawwal, I hope it's not too late to wish happy Hari Raya Idul Fitri to all Muslims. And as you all know, on 1st June tomorrow, there will be a total lockdown for Malaysia. And I would like to wish all of you the best during the lockdown. Stay calm, stay safe, stay healthy, stay at home, and most importantly, stay productive anywhere you are. Last week, we had a YB Datuk Haji Ahmad Azad in a special session on next Monday TED Talk. Apparently, he's MC for Terengganu. And again today, we will have sharing from Terengganu, from me. And the topic for today's TED Talk is modeling of optimal energy management for battery electric vehicle with load segmentation. So before we start, let me give a brief introduction of myself. My name is Dr. Tengku Azman Tengku Mohd, responsible as head of department at Polytechnic for Terengganu. I spent 11 years working at College Community for Terengganu and currently 9 years at Polytechnic for Terengganu. I had my first degree in electrical engineering from UTM Kodai in 2001. And under HLT scholarship APT, I did my master at University of Nottingham, UK in 2010, and PhD in control and automation in last year, 2020 at UTM. And my supervisor is Prof. Dr. Muhammad Hassan. I believe he's watching right now with our UTM EV research team. Hi, Prof. My research interest is on EV, specifically BEV, power and energy management systems, modeling and artificial intelligence. In Polytechnic Terengganu, currently we have a collaboration research with Sister Unita on environmental research. These are the today's sharing outlines. First, I will start with the conceptual map of research work. What is BEV? Why BEV? What is EMS? Modeling of BEV. Design of EMS. Design of EMS. Some results, conclusion, and finally recommendation for future research. This is the conceptual map of the research. It is the proposed encapsulated solution to the EMS problem in BEV. The research is a multidisciplinary which involves automotive, control, power, as well as energy. So what is BEV, or battery electric vehicle? A BEV is an electric vehicle which is completely powered by rechargeable battery pack, also known as all EV, pure EV, or zero emission vehicle, BEV. There are basically three types of EV in EV family: the hybrid EV, plug-in hybrid, and BEV. The differences between them are as shown in terms of the downside of mechanical drivetrain, the blue box, okay, until it is totally removed in BEV, and the increased size of electrical drivetrain, the green box. Obviously, in battery pack size and the availability of plug-in chargers. The EV has a great potential as clean and sustainable vehicle due to high tank-to-wheel efficiency, approximately 50%, Simple design, less maintenance, zero local GHG emission, can be regulated to microgrid, vehicle to grid, vehicle to building, vehicle to home, and the trend of reduce of battery price and the growing interest in PNS is an advantage to the EV. So why BEV? So this figure illustrates the transition from global issue of emissions and oil dependency to the specific problem statement adopted in this research. Actually, the constraint of BEV is in the battery. The three limitations of battery are high initial cost, long charging time, and limited range, or best known as range anxiety among consumers. PMS has been identified as a promising way to extend the driving range. But what is a PMS? PMS, or Power Energy Management System, is a combination of PMS and PMS. PEMS serves to control and coordinate the power generation, energy storage, and power flow within components to achieve maximum overall system efficiency. EMS is an accumulation or integration of power over a given time period and deal with energy consumption and recuperation over a trip. So there is a time period in EMS, but in PMS, it deals with instantaneous power to satisfy the power demand. PEMS is a promising way to extend the range by managing and distributing the power and energy efficiently. However, the biggest challenge is to develop optimal PMS strategies in BEV because it has not been disclosed and always commercially known as the black box. And also past researchers mostly contribute on hybridization of PSS in BEV. So it's hardly found research on PMS with battery as the only source. This figure shows the typical PEMS topology for EV. It consists of three main parts: the power generation source, the energy storage, and the load. Power generation source includes ICE, internal combustion engine, ECU, auxiliary power unit, and fuel cell. And energy storage includes battery, ultracapacitor or supercapacitor, flywheel, hydraulic or pneumatic accumulator, and the loads in terms of propulsion and non-propulsion load. To maintain the availability and continuity of power and energy, it is good to have multiple sources of power and energy. However, the more energy storage available in the system, the higher the cost and complexity of the system will become. A new PEMS topology has been proposed for BEV, which considers battery as the only storage, which is high voltage and low voltage, and the management task is applied at the load side of the BEV, where electrical auxiliary loads were segmented into four: the comfort load, initial load, safety load, and luxury load. This is the adaptation of a PMS strategy from microgrid from a power distribution system. For example, load segmentation and load shedding, which is expected to improve the driving range of extra 20%. So the first task is to model the plan for BEV. The first part is on the to modeling the drivetrain. Okay, the first part is to model the drivetrain. Okay, by using the mathematical modeling or whiteboard model of BEV drivetrain. First, the performance objective is to be set, okay, whereby the preset performance of BEV model has been done with comparison among commercial BEV. So the BEV model is the Number 5 is the BEV model, and we compare it with other commercial BEV, whereby we decided the performance parameter for top cruising is 150 km per hour, acceleration time is 10.5, and the range is 100% for 100% DOD. Depth of discharge is 250 km, and 80% for 200 km. Then we use the equation to construct the model in MATLAB. So starting from battery and DC-DC boost, converter, inverter, we have to have inverter, three-phase inverter, because we are using CMAC motor, the gear, the wheels, and also we include the vehicle dynamics. And finally, for the sizing of the component, we are referring to the component data sheet, okay, such as a vehicle dynamic parameter, drivetrain parameter. This is for the Iris EV, the segment B segment, and battery pack, PMAC for Yasa 400, and finally the component efficiency. For the purpose of performance testing, the model was prepared in a closed-loop control system. It consists of 3 inputs: driving cycle, STP75, and DDC and accelerator STP. We go to the detail later. And then the plan of BEV drivetrain and vehicle dynamics, PI controller, and finally the monitoring system. Okay, after the drivetrain model passed the performance simulation verification, the next step is to include the auxiliary load. So 20 auxiliary loads have been selected to be included into the supply load topology. Yes. Okay, they are the basic auxiliary load spec for green vehicle. So initially, the auxiliary loads were attached based on high voltage and low voltage bus bars. The model will undergo simulation verification to verify the energy profile of BEV. And for the purpose of power and energy verification, the model will prepared in supply load topology, where it consists of high voltage battery, DC-DC boost and buck converter, high voltage and low voltage power buses, and drivetrain with control, and finally the auxiliary load. And the second task is to design the EMS, which includes 2 levels of control: the LLCC, low level component control, and HLSC, high level supervisory control. So this is the detailed workflow for modeling EMS for BEV. So the first part is the low level component control, load segmentation, and the second part is high level storage control by using the distribution of strategy algorithm. So for the first part, we come up with new topology segmentation of auxiliary load to improve the load organization. And the second part of high level storage control is we come up with new algorithm for energy distribution for optimal energy distribution. So these are the detailed part, the first part of load segmentation in low level component control. So by using this formula, we come up with the load prioritization table. So from this table, we can design the auxiliary load by segment, which is we have four segment of load: comfort, initial, safety, and luxury. So here's how load segmentation works. First, we cluster the auxiliary load, the 20 auxiliary loads into 4, and rank it by function. So the first rank is the initial load, the second is safety, the third is comfort load, and the fourth is the luxury load. And Third, we set the weightage based on the power usage pattern and operational type. And number four, equation and average power approximation by using the formula. And we summarize the load in load prioritization table. Okay. Okay, the next step is the high level supervisory control via distribution strategy algorithm. So the concept in this algorithm is that the lower the capacity of available energy, the stricter the energy rule will become. High level supervisory control will turn on and turn off the load based on the level of battery FOC. Okay, we have a few level of FOC, which is the first one is more than 50, between 20 and 50, and less than 20. Okay, but the way of limiting the energy is by considering the priority level of the load. And in this algorithm, we design 5 states of operation: the normal, distribution, comfort limit, safety limit, and load scheduling. And finally, the discharging and charging state of low voltage battery. And this algorithm cooperate with load segmentation to ensure the appropriate scheduling of load. The EMS cost function here is to ensure the optimal energy distribution. So the third task is to propose the PMS, which include high-level supervisory control using fuzzy rule-based. Okay, this is the detailed workflow for modeling PMS for BEV. The PMS, the first part is the PMS or the mode, the driving mode has been designed in parallel with the high voltage battery SOC during EMS. Okay, so that the driving mode and EMS will support each other in energy consuming role. Okay. So the second part of PMS proposed adaptive driving mode via fuzzy rule based. The best mode will be automatically selected based on 4 input variables, which is the acceleration limit, high voltage battery SOC, power comfort level, and the regenerative coefficient or beta. Okay, so I fuzzy use the PMS cost function to compute the best mode for each condition, okay, by using this membership function, and this is the surface block and the fuzzy block in MATLAB link. So instead of having individual driving mode, this is the comfort driving or EV driving or eco driving, we can have a single integrated fuzzy mode. So the result for the first part, we have the result for BEV drivetrain and auxiliary test with 7 tests performed. Okay. The first part for the drivetrain or propulsion load test, okay, we use a constant of 120 km per hour speed input as our input, and from this test we managed to get the target acceleration performance, which is from 0 to 100 km per hour in 10.5 seconds. So this is achieved by the model. So for the effect of auxiliary load, we use a constant speed of 120 km per hour constant speed input, and we compare the result without auxiliary load and with auxiliary load. So only 4 parameters is affected. There is some noticeable effect. can be seen on current, power, energy, and SOC plot. When we zoom on the same plane, we can notify that the increase in battery current is 30.4 ampere, okay, and 20.4 ampere increase in inverter current, okay, 12 kilowatt increase in battery power, and 8.16 kilowatt increase in tractive power, okay, and it's 8.1 and 60.3 watt power consumption increase in battery energy, and 0.15% decrease in battery efficiency. Next, the findings for driving cycle test. Okay, we use three driving cycle NEDC, which is the new European urban and extra-urban SPC75, US urban driving, and as well as the SEC, the US highway driving. Okay, we can see that the performance ability of the BEV model to track the driving cycle speed input is very well, and shows that the model has been designed with robust control. When we compare the basic model with auxiliary, okay, the one with and without the auxiliary load, you can see that the total range, okay, during NEDC is 250.5 feet, so it achieves the target range. But when we include the auxiliary load, the total range will reduce to 200.53 kilometers. And also on the regenerative energy, you can see that the highest regenerative energy is achieved during FTP 75. This is due to the nature of high braking start-stop during the urban driving, and the lowest is during highway, especially the FTP is only 0.123 kilowatt per kilowatt hour. Okay, we have two findings here during auxiliary load test. The first one is the energy validation shows that the model is a reliable model with a very small error, okay, which is less than 1%. And the second one, we come out with this energy distribution profile, okay, relative to battery output or BEV, whereby from this three driving cycle distribution profile, we only select NEDC for the next implementation of EMS due to the balance profile of between urban and highway driving. So for the next phase, we are only looking at this NEDC driving cycle. Okay. Next, for the second part of the work, EMS for BEV test, we perform 6 tests overall. Okay. Right. During normal distribution, okay, a low voltage battery can be in discharge or charging state. During charging, low voltage battery will act as a load instead of supply. That's why the energy consumption is increased, okay, and driving range is decreased. Okay, so that's why we have this negative figure down here. However, during comfort limit, 6.4% energy is reduced, and 18.1 range is increased during comfort limit, while 12.2% energy reduced and 10.4 range increased during safety limit. The energy is optimized with cumulatively 18.6% energy reduced and 28.5% range increase. Okay, and so for the Next result, okay, for PMS, for BEV test, we perform another 16 tests. Okay, for part 3. So the first 4 tests is during the comfort driving. So here we can see that the well track fixed reference, okay, the well track fixed reference where there is no acceleration limit, and also the net energy varies around the reference. But in EV driving, okay, we can see that there is a slight reduce in gradient due to the acceleration limit, and the net energy is less than reference. Yes. And the last one, during eco driving, we can see that the more reduced in the gradient, the speed gradient due to the acceleration limit, and the net energy is far lower than the reference. And on the same plane plot, the distribution of the net energy can be clearly noticed between the modes. The blue line is for the during the comfort driving, the red is during the EV driving, and the green is during the eco driving. And the last one, the figure shows 3 types of plot. Okay. Then the first one is during PMS off and EMS off. This is for the reference. Okay. ENET is net energy as our reference with marked with the dotted black line. Okay. And the second is the net energy when TMS is on and EMS is on, whereby this is the manual mode. This is the same as we have seen previously. Okay, and the last one is when we use I fuzzy instead of EMS mode, we use I fuzzy and EMS on. So we can see here I fuzzy net energy distributed on 3 locations. If you can see that the net energy for I fuzzy is represented by the purple dotted line. Okay, the highest is represented the comfort driving. The middle there for EV driving, and the lowest, okay, the lowest line here is represented the eco driving. So I fuzzy, it proves that I fuzzy mode has successfully satisfied all the cost function of PMS. So we did some benchmarking with published previous work. Okay, previous researchers only managed to report their work on battery current related stage to conclude the losses. But in this research, we have developed a complete BEV model to implement the PMS and calculate the increment in range. If you can see here, without SC or supercapacitor, the reduce in battery losses are around 15 to 13%. Okay, but with supercapacitor, the higher reduces can be achieved. But in our proposed work, in this research, without a supercapacitor, with battery is the only energy source, the work managed to get a cumulative of 18.6% and 28.5 plus adaptive driving mode. Okay, and that's all for. And the last one for the conclusion. Overall, the work has described a holistic approach to the problem of power and energy management strategy in the EV. The modeling approach involving multidisciplinary fields of study was done in such a way that the model could be translated into appropriate power flow and energy distribution topology. The second one is the combinational approach of LOC and SSC in NS and PMS does not only offer a different outlook to problem, but also an implementation platform that addresses all features of energy and power management in satisfying multiple loads with battery as the only energy source. So this approach is in contrast with the approach in many publications that usually split the study into isolated problems without justifying how they could fit in the bigger picture. Finally, for the recommendation for future work, future research, the number one, the subject plan is BEV with battery as the only energy source. There's possibility to expand the model with hybrid sources, such as capacitor, also high-speed flywheel, or even second unit of high voltage battery. So, number two, instead of B segment, we can also adopt different segments or even heavy transportation such as electric bus. Number three, the numerous vehicle pilot topologies could be studied. And at the same time, we can modify at any part of, for instance, modeling of new power electric converter, replacing electrical motor with different type of DC and DC motor, and modeling of new battery configuration. And the last one is we can use more artificial intelligence or even the hybrid of them. So I think that's all from me for now. So again, thank you for listening. Thank you for your attention. And thank you for watching. And thanks again to the MACE committee for giving me this opportunity to share my research. So if you have any questions, please do not hesitate to email me at the email below, azman@tkt.edu.my or Tengku Azman 78 at gmail.com. So that's all from me. Wassalamualaikum warahmatullahi wabarakatuh. See you again next time. Bye bye.